Okay, thank you for introducing me. I'm Kantaro Ohmori. And yes, and I start by thanking for giving me this opportunity to give a seminar at NYU. Today's title is Symmetry in QFT, Quantum Field Theory and Beyond. This talk will be based on two papers I wrote with Clay Cordova at Chicago University 2 years ago, and also another paper worked with Zohar Komorgotsky at the Summer Center and his students Bedakis and Sifrashi. This work was done last year. And this work will be substantially also influenced by many works I did with many courses listed here. Today's theme of the talk will be symmetry. And so symmetry is the universal organizing principle in physics, and it appears in any subfield of physics in various ways, like the hydrogen atom wave functions or the magnetizations or like standard model particles. So, like, and symmetry appears in various places in various ways. Okay, and I'm mainly interested in quantum field theory and related topics. So symmetry itself is, of course, an ancient concept. Yet in the symmetry in QFT is a still remains a very interesting subject even in 2021. And in the last decade, I think there were two main progresses, and one is the quantum anomaly or Hooft anomaly for discrete symmetry. So the Hooft anomaly have been thought for decades mainly for continuous symmetry. But recently people are paying attention to the discrete quantum anomaly for the discrete symmetry. And it turns out that it's surprisingly rich and useful. Okay, so it have been giving the new insights on the strongly coupled IR physics of some condensed matter systems or the gauge theories like QCD or Yang-Mills. Okay. Another point is the generalization of the symmetry. So, okay, so that's the attempt to generalize the concept of the symmetry without breaking many good properties the symmetry has. And one successful thing is the higher form symmetry proposed by this gentleman. But here, more recently, there's another concept called the categorical symmetry or non-invertible symmetry. And I think this can have a potential to become a new paradigm in the quantum field theory. Okay. So I have contributions on both points, that this discrete symmetry anomaly and also the categorical symmetry. So I'm going to talk about both. Okay. So this is the outline of the rest of the talk. So I first review some basic concepts regarding symmetry in quantum field theory, including the Hooft anomaly. Then I'm going to talk about the constraint coming from the quantum anomaly of the discrete symmetry and its relationship to the gapped phase based on the papers with Clay Cordova. Then I will move on to the next topic, which will be the categorical symmetry and its relationship to the confinement in 1+1 dimensions. Okay, so the most important theorem regarding the symmetry is the Noether's theorem, which relates the symmetry with the conservation law. And for example, if we thinking about the translation, that gives rise to energy or momentum conservation, and the rotational or Lorentz symmetry gives the concept of the angular momentum spin. Okay, so these are obviously very important. Okay, in quantum system, the symmetry, if you have a symmetry group G, then for each element of the group, we have some operator acting on the Hilbert space of the system. Okay, and by that action, this Hilbert space becomes a representation of the group. Okay, and also the conservation law means that this symmetry operator UG commutes with H in this fashion. Okay, now this symmetry group should act on H in the consistent way. Namely, if we have two elements from the group, then this product for any state, this product of the operators should give the equivalent state that of this operator U of G1, G2. Okay. However, there is a subtlety here because in the quantum mechanics, the two states should be considered to be equivalent if the states will differ only by a phase. Okay. So actually, the most relaxed consistency condition here is that this UG1 times UG2 is equal to UG1, G2 up to a phase, and this phase can depend on the group elements we are considering. And this phase is called, I call it the projective phase. And I think first considered by Wigner in many years ago. Okay, and one important point is that this alpha should be independent of the state. So it should, in other words, this is the property of the pair of the system and its symmetry, and not the property of a state. Okay. Also, it is robust against the deformation of the system. This is because mainly because the consistent projective phase comes in discrete fashion. There is no continuum deformation of the projective phase. Okay, and these two facts, that the alpha is independent of state and also robust against deformation, means that we can use this projective phase to constrain the spectrum. Okay, so let us look at a very simple toy example, which is two-state quantum mechanics. So just think about the two-dimensional Hilbert space and think about the symmetry Z2 times Z2 generated by these matrices. Okay, so these matrices squares to the identity. However, these two matrices does not commute with each other, and this product gives a phase. So this A and B does not quite represent the Z2 times Z2 because it doesn't commute. However, the discrepancy or the failure of the multiplication law is just a phase, okay? And that's allowed in the quantum system. Okay? So this phase is nothing but the projective phase I've talked about, and this projective phase implies the degeneracy in the system. Okay, indeed, if we impose the Hamiltonian to commute with both A and B, then it's easy to prove that this Hamiltonian has to be proportional to the identity. Okay.
May I ask? So
yes.
Is it equivalent to say that the group is not Z2 times Z2, but there is additional element corresponding to this -1? Is it just equivalent language, or is there really principal difference?
So yeah, the point is that you can regard this as some non-abelian group, including -1. However, -1 is a phase, so just the proportional to the identity operator, not some random matrix. That's the important point. And so yes, so if we were using some Lagrangian or describing this system, like using a fermion or something, then you naively think that this symmetry is Z2 times Z2. And this project, yeah. So the point is that this discrepancy comes only as a phase. And the phase does not mean much in quantum mechanics. That's the point. Okay. Okay. But this projective phase can, means the degeneracy. So actually, even without even more complicated system, but if we have a Z2 times Z2 symmetry with this type of projective phase, then we can show that every state comes with a pair as a pair, and every state have a exact degeneracy as long as the Z2 times Z2 symmetry with projective phase is preserved.
Sorry, can I ask a very naive question just
Yes.
to make sure I understand this example? So the Hilbert space, this is supposed to be a two-state quantum system, at least.
Yes, yes.
So the Hilbert space is not really C2, it's a projective space itself, isn't it?
Hilbert space is just a two-dimensional.
It's a two-dimensional, it's a quantum system with a two-dimensional Hilbert space.
Yes, yes.
But that's not C2, that's a projective space, right? Precisely because quantum states don't care about the phase.
Oh yeah. I mean, the states up to the phase is characterized by the projective space. That's you're right. Yes.
Right.
So the point is that on the projective, on Hilbert space C2, this acts non-trivially as -1. But if you care about some projective phase which is C2 over the phase U1, then this matrix acts trivially on this projective phase. Yes.
Right. So why does it matter? That's what I'm confused about.
Yeah. It's well. Okay. Still this projective phase matters, and yeah, one way to say is that you can explicitly see that there's no way to resolve the degeneracy. There's another action that another obvious action that for each C2, the Z2 times Z2 acts as a flip, okay? -1 for each Z2. And that action, with that action, says nothing. So the two states can have arbitrary energy difference.
Right.
However, for this,
that's because that really doesn't do anything. That's multiplying each component by a phase.
Yes. But
okay.
But my point is that this phase is an information, an important information.
Shouldn't there be some way to reformulate this in the language where you start off with this projective space where you've already modeled out by the phases? It might be a little bit less confusing. Because part of the symmetry you're imposing isn't actually a symmetry. It's just the usual phase degeneracy in quantum mechanics, isn't it? So it seems like there might be a better way to present this where you've already modeled by the phases.
Yeah, so the point is that Z2 and Z2 acts on the projective space. However, but the point is that you cannot lift this action of Z2 times Z2 on P to Z2 times Z2 on H. Okay. And whether you can do that or not is an information.
Okay, go on.
Yes. Yeah, of course, I can use some fancy language like the group homology to characterize this phase, but I'm avoiding doing it. Okay, so yeah. The point here is that this the phase implies the degeneracy. So okay. Okay, so this is this is about the quantum mechanics, and this projective phase actually in the modern language can be thought as the Hooft anomaly in the 0+1 dimensional QFT. Okay, so in higher dimensions, the Hooft anomaly is the generalization of this kind of phenomenon. Okay, and one way to define the Hooft anomaly is to consider the partition function with the coupled with the background gauge field. This is just a background. We are not integrating over it. And if we do the gauge transformation for this background gauge vector potential, then even if the Lagrangian is invariant under such transformation, you might get this kind of phase from the measure of the path interval. Okay, and this is the generalization of the projective phase in quantum mechanics into the higher dimensional QFT.
Can I ask you just a terminology issue to follow? I don't know what's Hooft anomaly. I know Adler-Beljakiv anomaly, axial anomaly. I also know trace anomaly. What is Hooft anomaly?
Okay. Here I specifically talking about the anomaly for global symmetry. Okay.
Yeah, I'm also talking about global symmetries.
Yes, and I'm not. I mean, there are also the gauge anomaly, which is the consistency condition that always true for any consistent QFT. But that's different. I'm talking about the global symmetry, Hooft anomaly for global symmetry, and for example, without turning on the background, the conservation law is perfect for this kind of anomaly. So it's also different from ABG anomaly. So for this case, the symmetry is really broken by like this case, like the conservation law is broken by an operator. If this F is the dynamical gauge field, then the conservation law is really broken. That's the ABG anomaly. I'm not talking about that. I'm talking about the case that the partial mu J mu is some might depend on the background. But if background is turned off, it's 0. So without background, the conservation law is perfect.
Well, it's the same thing. It's the same thing. I mean, if gauge field is not there, then there is no anomaly. I'm not sure.
Yeah, well, there's a bit of difference here. If small f is dynamical, then this is not conserved at all. Okay, if this is just a background, then if you don't turn on background, this J is the very good symmetry.
Well, in equal way, you can say that if there is no small f, there is no anomaly. I mean, if I start with a theory in which there is a global symmetry which is not gauged.
Yeah. Yes, you're right. It's just the difference between you're gauging f or not. Yes.
Then this is just a standard axial anomaly we're talking about.
Yeah. You can think in that way. Yes.
And then when you said the phase is coming from the measure, in that case, it's measured due to the fermions, correct? Am I understanding?
Correct. Yes. Yeah. I should say that that's one way to get the anomaly, but yes.
Just Greg, maybe one comment. Well, like in QCD, there is axial anomaly for U1 axial current, and that current is not a symmetry. But there is also Hooft anomaly for SU3 cross SU3 chiral symmetries. Those are true symmetries. I think that's what he distinguishes.
Yes.
Then that's why I asked the terminology, because all of them are axial anomalies. In case number 1 that Sergey you just said, the current is external to the Lagrangian, which is that it's not, the symmetry is not gauged in the Lagrangian, but it couples to the photon, of course, and that's why you have anomaly, as opposed to in the other case in which the current itself is gauged in the Lagrangian. So, but by essence, it's all the triangle diagram. And I don't know why, maybe I'm behind the modern terminology, but this is the triangle diagram, and that's Adler, Bell, and Jakiv, and first calculated by Len Rosenberg at NYU, by the way. So anyway.
No, but the terminology is a Toft anomaly matching condition. I think that's
Yes.
origin.
That's
origin.
That's a very different thing. That's anomaly matching condition. That's a statement about spectra in the UV and IR. And I haven't any of this. We're talking about anomaly here.
Okay, I'm going to talk about the matching condition soon, and I'm distinguish these two concepts because for only one of them we can use the matching condition. Okay. Okay, but yeah, so we've already discussed the one. I mean, elementary example is this triangle anomaly. Okay, and so yeah, to put anomaly matching, which means that the anomaly which means many things, but in particular, anomaly in UV and anomaly in IR is the same. Okay, so the one typical use case is in the asymptotically free gauge theory, where the UV is weakly coupled, IR is strongly coupled. Then you can compute the anomaly in UV, and that should be matched by the anomaly in IR. Okay, and that constrains the possible IR physics. And these have numerous old applications, but also new ones, and new ones mainly coming from the discrete symmetry anomaly. And in particular, this paper, these guys applied the Hooft anomalies for the time reversal symmetry, which is discrete, and says some non-trivial thing about the phase of the pure ion Mills theory, which was, I think, very interesting. And the important point is that this Hooft anomaly matching condition, of course, gives information beyond the perturbation theory. Okay, so then let me go on to the one of main topics. Okay, so the main usage of the Hooft anomaly matching condition is that first you come up with some candidate IR EFT, and then try to match try to see that whether that can match the anomaly with the UV. But that's I and Clay wonder that is there any more systematic prediction? Sorry, coming from the anomaly, rather than just a tool of the trial data. Okay, so the question was that given an anomaly, what can we say concretely about possible IR behavior? And the one immediate thing is that if the UV have a non-trivial anomaly, Hooft anomaly, then IR fixed point cannot be trivial. So there has to be something in the IR. And in many cases, it is some gapless mode or massless mode. And in that case, the IR fixed point is a safety. However, for the discrete symmetry case, it sometimes happens that the IR does not have any gapless mode, but some topological degrees of freedom. In that case, the IR fixed point is a non-trivial topological field theory, which I will talk a bit more about briefly. Okay, but this latter option is not always available. And example is again for the continuous symmetry for the triangle anomaly. So starting from some anomalous word identity of the J 3-point function, the del J, JJ, and we can integrate this 3-point function and say that the J 3-point function is non-zero at the separated points, X, Y, Z, when X, Y, Z are definite points. You can say that it's non-zero in general, and such separated correlation function cannot be realized by TFT. and there has to be some massless degrees of freedom. And that shows that with the presence of this triangle anomaly, the Hooft anomaly, triangle Hooft anomaly, it should flow to the gapless IR mode. So in the case of the QCD with massless clock, of course, this massless mode is the pion. Okay, so let me briefly talk about the TFT, topological field theory. So topological field theory is in this context, we think this as an effective theory describing a non-trivial but gapped fixed point. Okay, there is no propagating degrees of freedom in deep IR if it's gapped. However, it can have multiple degenerate state on a compact manifold. So if the special time slice is compact, then and have non-trivial topology like TD, then the TFT have multiple degenerate state. Okay, and such degenerate state can be called the topological degrees of freedom. And accordingly, if we compute the partition function on some compact spacetime, then we get some non-trivial number, and like this. Okay, and such partition function on a compact spacetime depends only on the topology and or the manifold, hence the name topological field theory comes. That's this thing. Okay, going back to the anomaly. So in the case of the discrete symmetry anomaly, there are actually three possible IR. In most general case, there are three possible behavior. One is again the CFT. Then the second possibility is a spontaneous symmetry breaking of this discrete symmetry. For this, if this is discrete, it does not lead to Gaussian boson. So it can be, so it can just SSP of discrete symmetry with a gap. And the last possibility is the symmetry preserving TFT. So the discrete symmetry might not be broken, but the anomalies might be matched by non-trivial TFT. Okay, the question is when this last possibility is available. And in 2 dimensions, the last possibility is not available simply because there is no interesting TFT in that dimension. But on the contrary, in higher dimension, higher than 2, then Witten and his collaborator have actually shown that for any anomaly arise in the bosonic system, where the bosonic system means that the system does not include Fermionic operator. All the operators are even spin. Okay. Sorry, the integer spin, I meant. Okay. And in such case, they've shown that there is a symmetry preserving TFT matching any anomaly. I mean, given anomaly, they could construct a symmetry preserving TFT. Okay, so this means that in these cases, we cannot say something's easily measurable about the IL. IL might be some funny TFT, and we cannot say that there has to be gap massless mode or spontaneously broken symmetry or nothing. We cannot say.
I mean, unless this is too much of a disruption, it would be very helpful to have a concrete example of, one example field theory, for instance, of this phenomena. Well, in that context, I mean, probably this is not what you're talking about, but what I'm confused is, let's say I have n=1 super Yang Mills.
Yes.
And there is U1R, of course, right? And that, which is continuous U1, which by the ground state is broken down to the discrete symmetry.
Yes.
To Zn, but it is also broken by anomaly.
Yes. So that's
an example,
that's an excellent question, and actually is outside of this theorem. and I'm definitely going to talk about it.
Okay. But then for this, perhaps, some similar example or some example that.
Yeah, so in some example, like say gauge theory with multiple fundamental, let me see. Yeah, gauge theory with multiple fundamental fermion, then some discrete group of the axial symmetry is preserved. However, there is a way to match that, and there's a way to match that the discrete subgroup by some TFT. That if we add some scalars and try to gap it out, it's a bit complicated procedure, but I can gap it out without breaking the symmetry, this discrete symmetry. That's one example. Yeah, but for the n equals 1 super maze is outside of this because it's fermionic. It's outside of this theorem, and the converse is going to be 2. And the opposite going to be 2. I'm definitely talking about that. Okay, but here, before our work, myself, the perception that's the most anomaly for discrete symmetry in high dimensions can be matched by symmetry preserving TFT. So it doesn't have a very strong power to say something definite about and easily measurable about the IR. Okay. Okay, but there are some remaining situations, and one is this discrete symmetry anomaly for the fermionic systems. And in some cases, we could show that the opposite is true. So in a particular case, for a particular anomaly A for this discrete symmetry, in fermionic 3+1 dimensional QFT, and that anomaly cannot be matched by a ZK preserving TFT. Okay. So in other words, if this particular anomaly, which I'm going to explain, exists, then the possible IR phase is either spontaneous symmetry breaking or the gapless. Okay. Okay. And so the application is this anomaly is carried by various gauge theories when the representation of the matter is not fundamental. So let me explain this. A is something like the U1 ZK reduction, just a reduction of U1 and graph. And not U1 cubed. This is important. The A is ZK reduction of this linear anomaly. And okay. So for example, if we consider this SUN gauge theory with clocks in adjoint and say multiple clocks, then this U1 axial is broken down to some this discrete symmetry by ABG anomaly, but this still remains, and this has this kind of anomaly just coming from this diagram. Okay, and the theorem says that if you assume it's gapped in IR, then there has to be NC vacuum. Okay, and if NF equals 1, as pointed out, this is super males, and the grain condensate definitely do this but makes this vacuum. Okay, but the theorem, of course, does not assume supersymmetry at all. So applies to higher NF. Okay, if of course the too large NF it is going to be gapped, so it's going to be gapless. So, but probably for NF equals to 2, it's believed to be gapped, and this theorem ensures that there has to be NC vacuum. Okay. Any questions so far?
So why you say that there is a general theorem to Witten and others about bosonic systems?
Yes, yes.
So what's the difference between bosonic systems and fermionic systems? Why it's important that these symmetries in a bosonic system?
Yeah, excellent question. I don't have I don't have a very good intuition that can be explained immediately, but it's, yeah. But the point, yeah. Yeah. But in Fermionic case, in this case is like when compactified on some particular manifold, like the K3 or some funny manifold, then with under the presence of anomaly, we are going to get some Majorana fermion zero mode, and that kind of fermion zero mode and gives some very concrete obstruction against the symmetry preserving TFT. I think I don't have, sorry, I'm going to skip the sketch of the proof, but yeah. Yeah, okay. In other words, their proof, depends on some concrete lattice construction that approximates this TFT. But for the Fermionic system, such lattice realization of anomaly becomes complicated. That's one way to say. Yeah. Okay, so if there's no other, oh yeah, so summary of this part, again, this particular anomaly A cannot be matched by a ZK preserving TFT. So if this anomaly exists, then either there is a multiple vacuum or the theory is gapless. Okay, and the proof I skipped, sorry, is coming from the abstract constellation anomaly combined with some strong math theorem on the surgery theory. And I emphasize that this gives a strong implication like the number of vacuum in the IR physics, even for the very strongly coupled system, because this only depends on the anomaly and that has application to gauge theories. Okay. So if there's no other questions, I move on to the next topic. 2 minutes left. Fine. Which is categorical symmetry and the confinement, deconfinement in 1% dimensions. Okay. Before talking about the categorical symmetry, I have to talk about the topological symmetry operator corresponding to ordinary symmetry. So here, first let's think about just U1, ordinary U1 symmetry. Then we can define the symmetry operator, topological symmetry operator U, depending on this phase alpha, and living on the codimensional surface sigma of spacetime. Okay, and this is just defined by the exponentiating the natal charge. So natal charge is just integrating the current normal to the surface. The standard definition, and of course the conservation equation sets that this symmetry operator on natal charge is topological. So we can deform this sigma topologically without changing the correlation function. Okay, so this is some expression, a way of expressing the conservation law combined with the locality. Okay, and this symmetry operator implements the symmetry action in this way. So if we have some local operator or Q with charge Q, U1 charge Q, And if this symmetry operator encloses this local operator, because this is codimension 1, so it can enclose and shrink. And if you shrink this symmetry operator, we get this phase. Okay? Coming from the contact term of J and this operator. Okay, so this is nothing but the U1 action on this operator. Okay, good. So this is about in the case of U1 symmetry, and this generalizes to any symmetry. So any, any global symmetry I'm talking about. And for symmetry group G, even if it's discrete for each element of this group, there is a corresponding topological symmetry operator, UG, living on again the codimension surface. Okay, for example, if we think about Z2 symmetry in Ising model, and even we can think it on lattice, then we can define this corresponding Z2 topological line by flipping the coupling of the spins going across this line. So these couplings are sign of these couplings are flipped. Okay, and this configuration is just equivalent, or they give lives the same number with just this configuration where I flipped the spins inside the line. And this is topological because we can, again, just deform this red line like this. And I flip the spins where this red line passes through. Okay, so in this way, I can just deform this line. Okay. This is just an example. Okay. And these symmetry lines have, or in general, the topological operators have a fusion product, which is just bringing the two operators and smash with each other. And for this kind of symmetry operator, this fusion rule is just given by the group multiplication law. In particular, there is an inverse. So for any UG, we can find its inverse because it is a group, and the fusion of this UG and the UG inverse is a trivial operator. Trivial operator means that the same as not inserting operator. Okay, so this is the topological symmetry operator. Okay. However, not a topological operator in QFT, in general QFT, does not necessarily have its inverse. Okay? So such topological operator is called non-invertible topological operator. So invertible topological operator corresponds to ordinary symmetry, but there is another type of topological operator that is non-invertible. Okay, and example can be found in the critical Ising CFT in 1+1 dimensions. Okay, of course, this have the Z2 symmetry line that I described. However, there is another topological line that implements the Kramers-1 linear duality. Okay, so at the critical point, the Kramers-1 linear duality is the self-duality. And there is actually, at least in the continuum, this Ferrin found essentially found the topological line operator that implements the duality, but it does not have any inverse. Okay? The closest thing is itself, but the L sigma fused with itself gives not just one, but the sum of the trivial operator and the Z2 line. Okay. So in this sense, this L sigma, the duality line, is non-invertible. This is the most elementary example of non-invertible topological line, topological defect line. Okay, and the categorical symmetry is just referring to the whole set of topological operators, invertible or not. Okay, so in the two-dimensional QFT, the data of the topological line operators, which is also codimension 1, is in some case with finiteness condition, it's described by the mathematical concept of the fusion category, hence the name categorical symmetry comes. And in the 2D diagonal Rcft's, the Fehring found that topological line for each primary O of the Kähler algebra. And this Fehring line gives the important examples of the fusion category. Okay, and so this have been known for decades. However, the recent perspective is that this fusion category should be understood as a generalization of the combination of symmetry and its anomaly.
Sorry, what is the, how is the operator, the line operator LO defined in terms of the primary? What is LO?
Okay, good. So, yeah, he considered that so think about some line operator into the Rcft. Okay, and he wanted to classify some line operator that commutes with any Kähler algebra element. Okay, so he W is any Kähler algebra element, and he postulate that this line commutes with, so this Kähler algebra element pass through this line. Okay, and this condition is like it's like the Cardi condition for this condition can be mapped to the boundary, finding a boundary of this Rcft tensored with Rcft bar. Okay, and this, and if he put this Kähler algebra element from the first copy, and then this should be reflected as the Kähler algebra element for the second copy, like just folding this picture. So the point is that this finding this kind of line operator, the problem of finding this line operator is mapped to problem of the special type of boundary condition for this product Rcft. And then the story goes like the Cardi, the classification of boundary conformal boundary condition. And so similarly, for the Cardi story, the boundary state in the Rcft is classified by again the primary, and here there is a similar story.
This line the first example that you gave with standard symmetries was a bit special, right? Because your line operator was defined in terms of an integral of a local operator of J, say.
Oh yeah, for the continuous case, yes. For this L is not like that. This is like the generalization of finite group symmetry, so it cannot be like the integral of local operator. Yeah, thanks for the question. Okay. Yeah, so the recent perspective is that we should regard these topological lines, non-invertible topological lines, as a generalization of symmetry, and because in particular because this set of topological lines are preserved on an RG flow, and as the symmetry and anomaly does. Okay, so we can, in other words, the IR physics should admit all the topological operators that UV theory has. Okay, so in that sense, we can use this categorical symmetry in a similar way to the symmetry and its Hooft anomaly. Okay, and first first gauge theory. Of course, this in particular, this paper have some nice example in the the perturbation, conformal perturbation of Rcft, but we gave a first gauge theory example of such RG flow, which is 1 plus 1 dimensional.
Are there higher dimensional examples or?
Good question, and not many. It's the subject is in its infancy, I'll say. So not many examples yet. I'm going to talk about it at the last of this talk. Okay, so we thought about SUN gauge theory with masses Majorana fermion in adjoint representation. This is Lagrangian with the current J, and the point is the symmetry is just this discrete symmetry, and of course there's no Z, by the way. And the big question asked in 90s, actually in these many papers, was that whether this theory is in confined or not, in the confined phase or not. Okay, so naively, if you consider this fundamental Wilson line, then this adjoint psi cannot screen. There's no way to get the fundamental representation out of adjoint. Okay, so naively it's confined, but these authors said otherwise. Okay. So we don't have much time. Yeah. Let me think.
You can take an extra 5 minutes if you need it.
Okay, thanks. Yeah, so I go quickly. Okay, so this theory have a Zn center symmetry because the Zn acts trivially on adjoint, and that in modern language it's one form symmetry, and there's a corresponding topological local operator defined like as a disorder operator, and where this gauge field going around the infinitesimal loop around U, it evaluates to the center, the generator of the center here. Okay, and this is topological, and also the Wilson line is charged under this symmetry. In other words, this commutation relation with this phase. Okay, then you commute with H, Hamiltonian. So if you act on vacuum, then the vacuum is sent to be some superposition of vacuum because energy should be preserved. But U is also local, so local operator cannot send vacuum to another vacuum. Okay, so U has to be diagonalized by a vacuum. So that's a specialty out in the one form symmetry in 1 plus 1 dimensions. Okay, so if the theory is deconfined, namely the Wilson line has perimeter law, then this is non-zero state. In particular, it should include a vacuum as its superposition component. But from this commutation relation, we can say that the original state and this one state have different eigenvalues under U because of this. So these two states cannot be the same. Okay, and in this way, we can say that if this theory is deconfined, it's not confined, then there has to be at least n vacua. Okay. Then this gentleman found that if you consider this correlation function, like infinite cylinder, and you insert the topological local operator, then they found fermion zero mode, okay, which means that this correlation function is zero. With this configuration, okay. However, it's a bit hard to get the zero correlation function. So for this to be true, so yeah, they impose some particular boundary condition, and with that particular boundary condition at infinity, this infinite cylinder must prepare some vacuum here, the superpositional vacuum here, and that state should look like some superposition of this state with, and each state have the different eigenvalue under U. No, I should have said that U to n is 1. So these are the all possible eigenvalues. Okay. So this means that means that they've shown that there are at least n vacua, and this strongly suggests the deconfinement of the theory. Okay, so this was the old story rephrased in the modern way, but these authors, the Charman, Jacobson, Feinstein, recently revisited the problem, and they asked that how can this n vacua comes? I mean, there's only this small symmetry, and there's no way to get n vacua from the spontaneous symmetry breaking when n is large enough. So our answer, so we answered this question, and our answer is that this actually comes from the spontaneous symmetry breaking of categorical symmetry. Okay. So to find the topological lines and the categorical symmetry in agent QCD, we noticed that these authors essentially have shown that in fermions, the free fermion theory, we can construct the topological line like the Wilson line, but instead of gauge field, we integrate J. The current and up to some quantum corrections, which is in general complicated. Okay, and we've shown that this survives to be topological even after gauging this SN. Okay, and not so this comes for any representation of the SUN, but not all of them are independent. And we use some techniques from these papers and many follow-ups, and found that there are exponentially many such topological lines in adjoint QCD. So this number should be compared to the ordinary symmetry, which is just constant of n. But for categorical symmetry, there are exponentially many topological line operators. Okay, and the point is that this topological line operator looks very similar to Wilson line, and in fact we can just connect the two. Okay, so this blue part is topological, the red part is not topological Wilson line, and the fact that there is a line changing operator means that these two operators, the W and L, have the same charge under the one-hot symmetry. Okay, so if we have some vacuum, then if you act this topological operator on this vacuum, then again, because this is topological, so this is also a vacuum, and we can show that this is non-zero from the unitarity. Okay, so and have the different eigenvalue under U. So this state and this vacuum and this vacuum is not the same vacuum. Okay, so in this sense, this L box is broken. It's spontaneously broken. Okay, and it explains an n vacuum. Okay. So that, and it also shows that this W is a perimeter law, and the theory is deconfined. Okay. More detailed analysis actually shows that most of these exponentially many independent lines has to be broken in the analogous phenomena of the Hooft anomaly, and if we assume the theory is gapped, okay, and proven at least for the small n's, And this is consistent with the Hagedorn behavior anticipated by the Ktasov and his collaborators. Hagedorn behavior with temperature 0 at large n. Okay, so actually there are exponentially many vacua, not just linear in n. Okay, I skip here this. The summary of this part, we thought about 1+1 dimensional massless SN adjoint QCD, and it turns out it have many topological lines and categorical symmetry. Okay, and it can explain the deconfinement or the screening of the system. Also show that the system have exponentially many vacua, which is surprising. Okay, so the summary of the whole talk, I regard the symmetry as a general principle or the powerful tool to study the non-perturbative physics in quantum field theory. And we ask, there are two central questions. One is what can we conclude from the symmetry? And I present one strong theorem about it, that the IR physics constraint on IR physics coming from the quantum anomaly. And I also talked about the categorical symmetry, which is a useful generalization of the symmetry and its application. Okay, so the slogan is that I would like to extract as many non-perturbative results as possible from the symmetry in the most general sense. That's the slogan. So the future direction is that I really want to study the categorical symmetry in higher dimensions, and there's not many examples so far. It just people including me, just started to thinking about it. So, but yeah, but these authors already found an interesting example. So I think I'm optimistic about this. And I hope that this categorical symmetry becomes a novel method and for the studying in particular non-supersymmetric QFTs in this higher dimension. Okay, I stop here. So thank you for your attention.
Thank you. Thank you. So please ask questions.
So I'm ask. So in this adjoint QCD story, what happens when one adds fermion mass? Are all the symmetries broken there?
So when you add the fermion mass, yeah, it's asking. Yes, the categorical symmetry are broken. So then the system becomes confined, and we could also compute the string tension of the k-bound state of strings with a very small mass. Okay, so because the mass with the small mass, the categorical symmetry is broken, but by tiny amount. So still we can use it to compute the string tension of the confining string, which is actually like the tension is like sine pi. Okay. So pi. Okay, is like this is the tension for.
Is it the same answer which people used to get by bosonization in the past?
So for this sine law appears in many literature, but I'm not aware of the same result for this particular system.
Mm-hmm. But what happens with all these exponential number of vacua? Do they all disappear at small mass? How this transition happens? Or they they stay as metastable vacua?
Yeah, I guess so. Yes. With small mass, yes.
So at small mass, there will be a kind of landscape of exponential large number of metastable vacuum. That's
yeah,
that's the
yeah.
claim.
Yes, I guess so.
Interesting.
Other questions? I mean, I'd like to see the slides that you skipped when you talked about discrete symmetries and you were proving a result.
Okay.
Hmm.
So yeah, well, indeed, this is a bit technical, but so this anomaly A is carried by this single wire fermion in 3+1D, and just acted by ZK. And so it's okay. So in this particular case, from the measure of the fermion, if we do this global constant transformation, there's a zero mode on the general manifold. There's a zero mode acted by not trivially by this ZK. So this partition function can get this kind of phase with this ZK action, where this sigma tilde is essentially a signature, some topological invariant of this space-time manifold. Okay, however, this equation looks stupid because I was talking about the constant gauge transformation. So d lambda is 0. So A plus d lambda is for trivial reason A. So yeah, but still this equation holds. So what it really means is that when this topological number is non-zero modulo k is the k of the k, then this partition function should vanish. Okay, so this phase I first computed from this particular example of fermion, but should be universal for any system with this anomaly. So this phase is universal. So this condition should be universal for any system with this anomaly. Okay, so this partition function, some particular type manifold with non-zero signature should be 0. Okay, so for fermion, this is true because there is a 0 mode, but actually this should be universal for any theory with this anomaly. Okay, so and that's funny. I mean, we can show that the TQFT cannot have such behavior. Like, I use some very non-trivial math theorem like this, but the point is that this theorem shows that in 3+1 dimension TQFT, the absolute value of partition function is actually controlled given by this partition function of S2 times S2. And the information of this manifold actually only comes from the Euler number. So this itself is interesting result, but this combined with unitarity, and if this TQFT has a single vacuum on the first space, then we can show that this is non-zero. Okay, so for any manifold, and for the partition function is non-zero for the TQFT. So that contradicts with this vanishing condition from the anomaly. So that proves the theorem.
Thank you. Other questions?
Hello. Maybe this question is very naive, but you said that there are symmetries which have no inverse. Basically, if I do maybe this is dumb, but I do the overlap of two states, and basically if I do that symmetry transformation, then the overlap is not preserved. Does that affect basically the Born rule that gives us the interpretation of probabilities of the module square of the wave function? I mean, going to basic quantum mechanics, how I understand these symmetries if they have no no inverse?
Yeah. So yeah, some people don't want to call this symmetry, and yes. So yes. So this kind of non-invertible line going to project out some states. That's what typically happens. Yeah. So in that sense, it's not. Yeah. It does not preserve the probability in that sense. Yes. Yeah, but yeah, why I want this to I want why I want to call this symmetry is like I can use in the context of QFT, I can use this thing in a similar way that I use the ordinary symmetry. Yeah, but in the probe, yeah, you can say that it doesn't preserve the probability. Yes.
And are these emission, can these things be measured? I mean, maybe my questions are too naive because I don't know anything of this. Sorry, I don't want to interrupt, but I mean, are they physical in that sense then?
So what is, yeah, yeah, the conventional way to think about this is like the defect. So it's like, of course, the defect in general defect is not the topological, but you can think about the RG flow of defect. So the low energies of that defect is probably is characterized by this topological line. So yeah, that's a traditional way of thinking of it. So like some, I don't need. Yeah, this can be think even on lattice. Then it's like that you introduce some impurity and yeah, and then some property of the low energy state of the impurity is can be captured by this kind of line.
Actually, one question that I have is regarding your example of categorical symmetry with your adjoint QCD.
Yep.
Because at some point you have an explicit form for this L in terms of some currents, right? Some J's.
Yes.
So in this case, though, these L's are written in terms of local operators, right? So.
Oh yeah. Good point. Yes. So yeah. Well, here. Yeah. Okay. Yes. Yeah. It is written in the local operator in this case, and yeah. But the point is that it's not obvious at all that this is topological, and you have to do some complicated quantum correction. But yeah, so it's not like the U1 symmetry case that everything is obvious from the conservation law. But yes, it's in this case you can write in terms of local operators. Yes.
And now the second question is, since they are written in terms of local operators, are we discovering something new or something that follows from, say, some higher symmetry, W algebras, etc.?
So the W, so the W algebras exist only on the fixed point. So it's not at least obvious that it can say something about the adjoint QCD. While once we, yeah, and yes. And another thing is that yes, this is expressed in this in terms of local operators, but it's not actually very useful. And well, it's useful to see that there's a line changing operator, but actual computation is not useful. So yeah, that's one point. But yeah, I'm not exactly sure, but that it's not. At least it's not obvious that the the affine algebra directly helps to explain the confinement in adjoint QCD. I mean, without going through this topological line.
So these things don't form a group, do they?
So these things do not form a group. This
So
this L box, when n is greater than 2, this L box is not invertible.
right. So then the whole the Wigner program, you know, I mean, we take it for granted, but it's a remarkable thing that particles can be described as representations of some symmetry groups. Is anything similar that one can think of here, or because we're talking about states?
Yeah. So we can. Good. Yes. There's a kind of representation theory or something that. So the we can sorry. Let me see. Yeah, each state is in some kind of representation of yes. So for example, yeah, like yeah. So here there are many. I've said there are many vacua, and okay, and in a sense, this vacua is in a representation of or a module of the fusion category, and we can classify the possible module of the fusion category, and we could show that the smallest module is still have this many vacua because of the anomaly. So that's kind of the there's a sense of, I mean, the generalization of representation theory is going on.
Thank you.
You have so the what defines this L? So they are topological in the sense that they are defined on lines, but when two lines are
yeah, so it should commute with the stress energy tensor to that to be topological. So, and that's not obvious from the expression I wrote, but it's true. Yeah. Then the fusion is like, yeah, I mean, yeah, of course you can do some fusion. It's like L1 and L2, then R1, R2, then like. So if you fuse the two, then you get some just a tensor product of R1 and R2 as a actually as the affine algebra. Then okay, so let me write a bit precisely, like it, yeah, if R1 tensor R2 is N1 to K RK, then this one is like explicitly like sum over N1 to K of L. Okay. Yeah, but this is, I mean, this fusion coefficient does not, I mean, invertible in general.
Thank you. So other questions? Do you have any? So you talked a little bit about higher dimensional examples, and now how applicable are these methods to, say, theories like, I don't know, standard model QCD, where you have fermions, but well, not that many fermions, and also masses?
Yes, so I at this stage I do not know whether this categorical symmetry exists in some gauge theory remotely resemble to standard model. So I'm not, but what I hope is like to, is like at least there may be some new categorical symmetry with massless limit of the standard model or QCD. Then still it might still say something about the EFT in or some strings or something, and turning on mass can be still tracked by the perturbation theory. So something like that is like, so mainly about the EFT is what I have in my mind.
Thank you.
So how one would start looking for this categorical symmetries? Because for the usual symmetries, we know what to do, kind of look at possible transformations, live in action invariant. So what do you do here?
Good question, and I don't know. So yeah, so that's the big obstacle to ahead.
But for instance, in this example, how did you guys find them?
So these
What
guys,
was your,
yeah.
what was the thinking?
Yeah, so right. So this is like the U1 semi-direct SN, U1 to the N, so gauge theory. Okay. Then the non-invertible, they found non-invertible lines. That's like for here, there's a one-form symmetry. So,
But even in your case, in a joint QCD case, how did you find these symmetries? What was the guiding principle for you?
oh yeah, so in 1+1, the guiding principle for the Rcft, the guiding principle is actually the chance time realization. And yeah, I skipped, but yeah, one thing is that these people already know the explicit construction, but the actual techniques coming from representing some Rcft as a chance-Simon theory on interval. Then these topological lines actually, okay, so the fermions are like actually the Rcft of SUN level n, and like okay, let me skip the detail. I should talk about detail, but roughly speaking, these topological lines actually coming from the topological lines living in the bulk of topological theory, 3D topological theory. So in 2D, the guiding principle is that like to express the system as our topological theory with in higher dimensions and compactifying on the interval with some boundary conditions, and particular boundary condition which is not topological. Then these topological lines just comes from the bulk topological line. Okay, and
but then your theory is not CFT. Then you're gauging it, and you're saying that.
Oh yeah. So in here, first we consider the free fermion and classified all the lines in free fermion. Then next consider what happens when we gauge. That was how I did. Yeah. So the obstacle is that I don't know how to naturally couple in 2D Rcft, there's a natural construction from the 3D channel segments, but I don't know the analog in higher dimensional QFT or CFT.
Thank you.
Yep. Okay, thank you. Do we have other questions? Any
Questions?
If none comes to mind now, then let's thank Kantaro again for this.
Thank you very much for inviting and many questions.
Thank you.
It was
And so we can end it here. So thank you very much.
Thank you very much.
Thank you too.
Thank you.